All right, so let's go through these. Now, we worked a little bit on these Friday, and some of you weren't here, and I never went over the answers, so I'm actually going to take the time to go over these today. And these are electron configurations, and some of you are like, I have no clue what any of this is. So number one, it represents a noble gas. Just look through that and tell me which one you think it is. What do we know about a noble gas? Has a full octet. Which one of these up here has a full octet? D, very good. Number two, represents an atom in an excited state. What that means is an electron has moved orbitals. An electron has moved orbitals. So we got to look up here and we got to figure out which one is not where it's supposed to be. So if you look at some of these, do any of them look like that they're in positions they should not be? Look at A. Why does A look real funny? There's an empty orbital. According to Aufbau's principle, you remember that name? Remember we fill energy levels from lowest to highest, or we fill a roller coaster from front to back. Okay. Aufbau says you can't skip energy levels. So what did they do in letter A? They skipped both electrons, right? So they jumped way up. So A is the correct answer there. Yes? Yes. Hund's principle was, that's like Hund's house. Basically, you have to separate the electrons before you pair them. Remember, if I have three bedrooms for kids, and I've got 2 kids, am I going to put 2 kids in the same bedroom? I'm going to split them up, right? So it's up, 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 and then down, down, down. That was Hund's rule. Aufbau, Hun, and Pauli's exclusion principle. We didn't get a whole lot into Pauli because that has to do with it's their quantum numbers, and the quantum numbers are no longer tested on this, so you don't have to know quantum numbers. They have to start. You fill from lowest energy to highest energy. Okay. Number 3 represents an atom that has 4 valence electrons. Be very careful when you answer this. Four valence electrons. First of all, let's kind of look at it from this perspective. Let's look at B. What element would be B? It's 2s2. Do you agree? So if I wrote 1s2, 2s2, who is 2s2? It is beryllium. Very good. What group is beryllium in? It's in group 2. Does it have 4 valence electrons? All right. Who is 2p2? I know it'd be a whole lot easier if I had a periodic table, wouldn't it? Alex, Chase, do me a favor. The periodic tables are back there on my cart. Will you give everybody one? It is carbon. What do we know about carbon? It's in group 14, isn't it? So how many valence electrons does it have? It's got 4. So we know that the answer here is definitely going to be C. But let's look at why that's true. Remember, the first energy level can hold how many electrons? 2. Well, doesn't 1s take care of all of that? All right, the next one can hold how many? 8. Well, the B has 2, and then look at C. 1, 2, 3, 4. You see how that works? Okay. Just since we're going by it, what element is D? It would be 2p6. Who is 2p6? It is neon.
I have a question.
Okay.
When you do that, what do you which way are you going? Like, do you go across first? Or
Once you get the periodic table shape. Now, let me ask you something. We love these and we learn how to do it. What is this AR in brackets called? The noble gas configuration, which means you start at AR and then work your way forward, right? So what we're really looking at is 3D, and then how many in the 3D? 3D6, right? But what do we know about the D block? Remember, we got to lift it up, right? So it really starts on 4, but it really begins on 3. So count the very top row of the D block, which starts at SC, and count over 6. 1, 2, 3, 4, 5, 6. So who is it? It is iron. Very good. It is iron. Does that make sense? Yeah. You see how I did it?
So like when you got neon, you start in the P block and
Yep.
it's the sixth one over.
Yep, it's the
and
sixth one over.
Second down.
Yep.
Okay.
Okay. All right. 4 represents an atom of a transition metal. Well, that should be real easy. Why is it E? Well, it's D block, and it's what metal? It's iron. That's easy. 5 represents an atom that has an ion that will have a color in solution. Now, this one's kind of tough, but you guys don't know this. Ions that are color in solution come from transition metals. So, this is something that you may want to make a note of, that these are transition metals that have ion colors. So, who would it have to be? It's got to be iron again. Okay, that's something that you may not know, but I'm just telling you now that if it has an ion color from a solution, it has to be a transition metal. Okay, moving to the bottom set. First of all, before we go any farther, let's look and see if we can label these. A, 1s2, 2s2, 2p6, 3s2, 3p5. Who is 3p5? Who?
No,
It's chlorine.
you start from the H.
Yep, you always start from the top. Okay, 1s2, 2s2, 2p6, 3s2, 3p6. Who is 3p6? Yeah, argon. All right, 1s2, 2s2, 2p6, 2d10.
No, it's not.
Does that sound right or wrong? That's impossible, right? Well, that's interesting. Look at number 6. An impossible electron configuration. Why is that impossible? Is there a such thing as 2D? Remember, we always start at which D? 3D is always the first one we can have, right? That's why that's there. Okay, D, 1s2, 2s2, 2p6, 3s2, 3p6, and then 3d5. What did we skip? We skipped 4s2, didn't we? Okay, so let's just kind of hold off on that one. So let's kind of just make that note. E, 1s2, 2s2, 2p6, 3s2, 3p6. Now here, they do it a little different than I do it. They wrote the 3D in front of the 4s. Sometimes you'll see it this way. They just put them in numerical order. But it's okay. It is okay. So 4s2 and then 3d3. Who is 3d3? What? What? Vanadium. All right. So we good on all those. Now let's look at 7. The ground state electron... the ground state. Now, what does ground state mean? It's normal, non-excited. It's what you would write anytime we're talking about a regular old element. If I say, write the electron configuration of lead, it's what you would write. Or if I said of bromine, it's what you'd write. So, which one is the ground state of a transition? What? E, very good. Do you see how it helps to go ahead and label what element it is? 8. The ground state electron configuration of a halogen. What are halogens? Group 17. Well, now it's real obvious, isn't it? What's the answer? It is chlorine, which is letter what? That makes it real simple when you label them. Okay. Number 9. The ground state electron configuration. This is interesting. The ground state, which means it's not excited, of a common ion of an alkali element. Now, this is interesting. What does an ion mean?
Charged.
It's charged. But it's specifically referring to which kind of element?
The ground state.
An alkali. So if it's an alkali element, what group is that? Group 1. So what's this ion charge? +1. Do you agree? All right. So if it's plus, is it gained or lost? It's lost an electron. So up here, this electron configuration would have to represent an atom that has lost an electron. Now, why do all atoms gain and lose electrons? To become stable. What group? Which one up here is stable? Why is it B? Very good, because it's a noble gas. So, Which element specifically lost one of its electrons to turn into argon?
Potassium,
Why potassium?
because it has
19 minus 1 is what?
18.
Well, duh, that should make sense. So you see how this works? Okay? So we've gotten those. 10. Represents an excited. Now, what does excited mean? It's jumped up energy levels, right? Of a transition element. Well, we've already talked about one that got skipped, right? So what does that mean? It's jumped up some energy levels. So what does it have to be? It's got to be D. Everybody good on that? Okay. All right, so let's roll on to the next one. Are these the same ones? No, okay. This is actually a good one to talk about. So let's actually look at, and let's label the elements again. Number 1, do we have any clue of who number 1 is? Why not? Because it's missing one, right? All right, so we don't know who that is. Are these the exact same electron configurations as the top one?
Yeah.
All right, that's fine. We can do it anyways. All right, so we know that B is what element? It's beryllium. C, who is 2p2? Carbon, neon, and was it iron? Okay. All right, so represents an alkaline earth metal in the ground state. Now, what is ground state? That's normal and neutral, right? Okay. What does alkali earth metal mean? All right, well, who up there is a group 2? Beryllium. That's easy. Make sense? Okay. Atom that is paramagnetic. None of you have no idea what that means. No, I'm going to tell you what it means. One or more orbitals. Now, what is an orbital? A little line. Can hold another electron. Paramagnetic basically means how do electrons always want to be? They want to come in pairs. Paramagnetic means it needs another to gain a pair. So there's another alternate type. Does anybody remember the alternate type from paramagnetic? It's dimagnetic. And what does the prefix di mean? Which means it has its 2 electrons. So if you go back and you look, are there any of these up here that represents an atom that is paramagnetic, that has no pairs? What number is this? Is this number 2? It is C. Why C? Because if you look right here in the 2p, could there be an extra pair put in there? Yes, I know what you're going to think. Well, what about E? But what if you notice right there in that first orbital? There is something that has a pair, right? We're talking about the entire thing. There can't be any pairs. D has at least one pair. Do you see the difference? Am I just talking dead space?
Yeah.
You missed that one? All right, but so here's the difference. Do you agree that, all right, that's got a pair, right? But once you go to 2s, it's paired, it's paired, it's paired. All of these are paired, right? But when you hit this, it's 1, 1 blank. So there needs to be a pair in there somehow, right? Which means paramagnetic. But once you get to this part, the 3D, those are all empty, but is there at least one pair in that entire orbital? That's what dimagnetic means. That it has 2 pairs, or that it has its 2 electrons.
What about A?
Okay? Because it's one of those excited energy states. It's a little different.
It doesn't say in its ground state.
Yeah, but you can't really talk about excited.
Paramagnetic, it says one or more orbitals. What?
One or more orbitals that can hold another electron.
Hey, Charles. I didn't see
You with me?
Yeah, I feel like that doesn't say anything about an E. Another orbital could take it. What's it called?
Yeah, it's
So as a fact, it can't have any pairs at all.
exactly, can't have any pairs. Yep. All right, 3 represents an atom with a highest first ionization energy. Now, you guys, I'm just going to be honest with you. Sometimes there are answers to these questions that I just can't quite grasp. The answer to number 3 is A. And here's why I think it's going to be A. It's excited, which means not only is excited, to be able to remove it, you're going to have to pull it down back to the original and then pull it off. Does that make sense? So it's absorbed energy to get up. So not only do you have to add an additional set of energy, you've got to put in the energy that made it jump and then pull it off. So that is just one of the ones that I just can't quite grasp and understand and how to explain it to you.
My answer choices for that are different.
This is topic 1,
On
quiz 2. So it's BCA.
that is on my quiz 3.
This is?
Yeah, that.
Yeah.
Yeah.
Are we on quiz 3?
No, those choices are a part of it.
Really?
Yeah.
Remember when they were asking us the big arrows and if they meant something different? This is the one that they were talking about.
All right, so is this quiz 3 on the
Yeah,
paper?
but it's different. It's
It's the
different.
questions from quiz 2 and
Like
the diagram
two
from
things
quiz
are like
1.
swapped.
Oh yeah, it is.
So the picture was wrong?
Yeah.
What is different? Yeah.
On the paper it's different?
Yeah.
That's the problem. All right, so we're gonna go skip to this. So number 6 represents an excited electron configuration for an element that in the ground state would be dimagnetic. Now, this is a good question. All right, here's what's. All right, so let's just talk about what each one of these would be. A, helium, and then 2s2, 2p5. Who would that be? Who would that be? Who's 2p5?
Oh. I'm trying to figure out how to do it.
It is fluorine. All right. Who is 3p6? Argon. Who is 4s2?
Calcium.
Calcium. Now, what do you notice is weird about D? 4s is missing. So that tells me that something is being excited right there. And then finally, we've got E, which is 4s1, 3d3. What's weird about that? That means they jumped from 4s2 and it skipped one, right? So basically that one that was in 4s2 that's normally up and down, it jumped to the 3d. Does that make sense? Okay. So let's just kind of go from there and see if we can narrow it down. The
On this one, I open another app. What do I put in?
PDF. 7. The ground state of electron configuration for alkaline earth. That should be real easy. What's an alkaline earth? Ground state is group 2, so who's the only group 2? Calcium, very good. 8. The ground state of a halogen ion. What does an ion mean? Charge. So if it's a halogen, what's it going to turn into? -1. So did it gain or did it lose? It gained. So what do all halogens turn into when they gain one? They turn into noble gas. So who's your noble gas? B, right? Does that make sense? All right, 10. The ground state electron configuration. All right, so we know. Let me move this back. All right, so it's ground state of a common ion, again ion, of an alkali. What do we know about alkalis? What do alkalis turn into ion-wise? X plus, right? Well, what do all group 1s do? Do they gain or lose? They lose. So who do they turn into? The noble gases. Well, who's your only noble gas? Argon. So it's going to be B again. And then 10 represents an excited electron configuration of an alkaline earth metal. Now, so that means that is a group 2. This is a group 2 that has been really excited, right? But now, let's look back up here. 6 represents an excited electron configuration for an element in the ground state that would be diamagnetic. So we know 2 of them are going to be, hold on. Did I do these wrong? I feel like these are off. Represents. Yes. All right, guys. Let's. This is. Okay, I have no idea what just happened. I think I just lost everything that I just drew. All right, we've already. Okay, so we've already talked about this. The one that has one double bond is D. The one that has the most trigonal pyramidal is this one, which was E. The one that has one pair of undebonded was again this one because it had those and I've just drew them. And then it says the sp3 hybridization and symmetrical was the methane, so that was C. And then here's the part that I want to get to. The molecule with the largest dipole moment. Dipole moment means it is polar. So essentially what they're asking you is which of these molecules is the most polar? Water. Very good. So it is water. So the answer there is B. That makes sense? Okay. That's non-polar. Yeah, that's actually a good question because everything is kind of stretched out the exact same way. But it is polar. Excuse me, non-polar. This one, I can't even tell what all is supposed to be on this. But does anybody know what letter A is on this one? Is it different on y'all's as well? All right, I just want to cover this real quick, guys. And this is drawing Lewis structures because I want to make sure that everybody remembers this. If it's got a charge, there are 2 things you have to do. What's the first thing you have to do? Okay, you have to, very good, you have to add an electron if it's negative. Why are you adding an electron? It's negative, it's gain 1. All right, now if it's charged, what do you have to put it in? Got to put it in brackets. So let's start from there. So I've got S equals 1 times 6. I've got F equals 5 times 7. All right, so 35 plus 6 is 41. Now, so then I have to account for the 1 extra electron, which gets me 42. But what would throw up a red flag is if you stopped right there. It's odd. You can't have an odd number of electrons. So here's what we're going to do. We may have to adjust, but I'm going to start like this. S, F, 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 and F. And like I said, and you got to have the charge on the outside. So how many total electrons did I use? 2, 4, 6, 8, 10. So minus 10 leaves me 32. So every fluorine is going to get 6. But I've got 6 I've got 5 electrons, or 5 atoms, right? So how many am I going to use? 5 times 6 is 30. So that means I'm going to have how many left? I've got 2 left. So where am I going to have to put them? On the S. Very good. So let's look. Roll to the end. Now change this up.
How do you know how to change to the right shape?
Charles, you don't? 1, 2, 3, 4.
How do you know what the right shape is? That's the only one I have.
Here's let me give you an example. If you ever have lone pair, always put them on top and make everything bow out around it. That's honestly the best thing to do. So when you have this, you have A, B, 5, E, right? Okay. Hybridization, 1, 2, 3, 4, 5, 6. So you've got S, P1, P2, P3, D1, D2. So you've got S, P3, D2. This one would actually be polar based on 3-dimensional structure and so on.
Did you say that lone pairs always make it bold?
There's actually 2 exceptions to that. Let me show you the exception. One of them is square planar, and one of them is this right here. Everybody got this? In fact, this was 2 years ago, or 3 years ago now. One of the ones they did was I, 3 minus. So it was I. Okay, and then 2, 4, 6, 8, 10, 12. And then what happened is there were 3 lone pair around the central molecule. And so it really made this whole thing linear. So, which is nonpolar. The other example is if it's square planar, which means you have X, E, and I think this is an example, and it's charged, but I can't remember. And I think it 2, 4, 6, 8, and it's something like that. So I think it's like A, B, 4, E2. I think this is it. Yes, sir.
Can sulfur have an expander like that of 12? What is 10?
It can have 8. No, it can have 12. No, it can have 10. Did it? That was because it was an ion. Does that make sense? Okay. All right. What I'm going to do is I'm going to, and this really frustrates me because this next one was a picture of an electrolytic cell. All right, can y'all find this one? What I really need to do is just, either way, if I do it tomorrow in class, y'all aren't going to be able to see the difference.
I have a picture of this thing.
Really? All right, this is quiz 11. Like I said, if you would actually have the hand copy packet, this is quiz 11. So let's look at the definitions. The energy required. Well, that's easy enough, but however, these are all energies. Required to convert a ground state atom in the gas phase to a positive ion. So we're going from neutral to ion. So what energy would that be? Ionization energy. Very good.
Wait, what was that? I know that one.
Ionization energy.
No, what was the question?
It's number 7.
I know that one.
Okay. It's number 15 on y'all. Okay. The energy change that occurs in the conversion of an ionic solid to a widely separated gaseous ion. This is one y'all really don't talk about a whole lot. There's another name for an ionic solid and how it's formed in the structure. Yep, it's a lattice. An ionic solid is formed into crystal lattice. And so to take something from an ionic solid to a gas is lattice energy. It's the amount of energy required to destroy that lattice, okay, which is extremely, extremely high. 9. The energy in a chemical or physical change that is available to do useful work. Be very careful. What is the energy available to do useful work?
Free.
It is the free energy. Very good. The energy required to form the transition state in a chemical reaction. Now, what is a transition state? Remember, the transition state has to do with the thermodynamic graph. Where's the transition state? At the top. Well, what do we know about this little hill? What's that hill called? Activation energy. Very good. And so this is A. And then the temperature is the measure of the average of this energy. D. You've got to know that T is equal to KE. But are speeds equal to kinetic energy? No. Okay. If me and Jacob were going to run a race, who would run the race faster? That guy. But what if we were to run into walls at our maximum velocity? Who would hit with more energy? Physics people. The same. Why? The kinetic energy formula is KE equals what, guys? 1/2 mv squared. So if me and Jacob run into the wall, which one of those would be greater for me? M. Which one would be greater for him? Velocity. They will mathematically proportionality out to where our energies are the same at the same temperature. Now, if we're at different temperatures, then it'll be different energies. But the energy is the same no matter the temperature. But do velocities and speeds change? Yes. Does that make sense? Okay.